Alright, welcome back everybody. Here's the final example from this lesson, reviewing volumes of solids. This comes from the 2010 AP Calculus BC exam. It was question number 4, which is a non-calculator question. Got the region R, bounded by the graph of y equals 2 square root of x. That's that curve there. And the horizontal line y equals 6. So first we're going to do part B. Part B says to write but not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 7. So we've got this line up here, y equals 7, that we're going to rotate this region around. So we'll set up, we're revolving around a non-axis here. We'll go ahead and set up our integral. It's going to be pi times the integral from somewhere to somewhere. Now, since we're revolving around a line that's parallel to the x-axis, we want everything in our integrand to be in terms of x, and we want our limits of integration to be in terms of x. So we want the x-coordinate of the left-hand side of this region and the right-hand side of this region as our limits of integration. Those are going to be 0 and 6. And then the first thing we need in our integrand is we need the outer radius of the solid, which is the distance between the outer boundary of this curve and the axis of rotation. And I'm going to find that distance by taking bigger minus smaller. The line is higher than the curve, so I'm going to take 7 minus 2 square root of x and square it. That's our outer radius squared. And then we need our inner radius, and that's going to be the distance between the two horizontal lines, which is just 1. And there's our answer for part B. Part C. The region R is the base of a solid. And I'm going to erase some of my notations up here on my picture. The region R is the base of a solid. For each y, where 0 is less than or equal to y is less than or equal to 6, the cross-section of the solid taken perpendicular to the y-axis. So it's a cross-sectional slice like this, perpendicular to the y-axis. So since we're talking about a cross-section perpendicular to the y-axis, we want our integrand and everything about it. Oh my goodness, I just noticed I completely put the wrong limit of integration on that first integral. I wanted the x-coordinate. I just read the y-coordinate. Sorry about that. Sidetracked. So since we're talking about the cross-section of a solid perpendicular to the y-axis, we want our limits of integration and everything to be in terms of y. We're supposed to write but not evaluate an integral expression that gives the volume of this solid. So things that I need to do, I need to solve and get the equation for this curve as x equals a function of y. That's simple enough. We divide both sides by 2 and square both sides, and we get that x is equal to y squared over 4. Okay? And then what I'm going to do is I'm going to draw a picture to help me understand this for part C. I've got a solid where the length of the solid is based off of that curve. It's y squared over 4. And the height of the solid is always 3 times the length of its base. So that's going to be 3y squared over 4. And if I find the area of this rectangle, that gives me the cross-sectional area for in my integrand. And so this is going to be the integral of the cross-sectional area, which is 3y squared over 16. And now, all I need to do to find the volume of this is put in the limits of integration, and they should be the y-coordinate at the bottom of the region and the y-coordinate at the top of the region. And now's the time for those limits of integration to be 0 and 6. Alright, So anytime we're finding the volume of a cross-sectional solid, we need to make sure we pay attention to which axis the cross-sections are perpendicular to, so we know which variable we need to use for the limits of integration and for the curves. And then it's just a matter of drawing a sample cross-section and filling in the dimensions of that cross-section based off of the information that we have, and then finding the area of the cross-section. And the area of the cross-section is going to always be our integrand whenever we're finding the volume of a cross-sectional solid like this one. Alright, that's it for this video and it for this lesson. See you guys next time. Hope you have a great rest of your day.